Hello everyone, welcome back to a new episode of Advanced Code. We're going to do day 11 today. Day 11, Chronal Charge. You watch the elves and their sleigh fade into the distance as they head towards the North Pole. Actually, you're the one fading. The following sensation returns. The low fuel warning light is illuminated on your wrist-mounted device. Tapping it once causes it to project a hologram of the situation. A 300 by 300 grid of fuel cells and their current power levels, some negative. You're not sure what negative power means in the context of time travel, but it can't be good. Each fuel cell has a coordinate ranging from 1 to 300 in both the X and Y direction. Top left is 1, 1. Top right is 301. Fine. The interface lets you select any 3x3 square of fuel cells. To increase your chances of getting to your destination, you choose the 3x3 square with the largest total power. Okay. So we're choosing a 3x3, okay. And there's some formula which is, given a fuel cell, we can calculate a power level in the following way. So the rack ID is X coordinate plus 10. Start with a rack ID times Y. Add the grid's serial number, which I guess is just a single number? Yeah. Okay. Set the power level. Okay, multiply the power level by rack ID. Keep only the hundreds digit. Okay. And then subtract 5. All right, so we need to choose basically a starting, we'll choose, let's say, a top left coordinate, right? We only have to choose one point, and we can let that determine the entire 3x3 grid we're selecting by just adding 2 to each coordinate, right? Yeah, and that's indeed what they're having. They're even hinting us here. What is the XY coordinate? Oh, interesting. I would have guessed that they might ask me. Nor they don't usually ask for compound values, right? I would have guessed that they would ask for a number, like, say, multiply the two coordinates together or something. But okay, so this seems pretty straightforward. We just need to read the input in to get a grid. And then iterate. Yeah. Do I need... I don't need an array, but we learned how to build an array a while ago, so it could be kind of fun. I don't know, though. I don't really need statefulness for this. I'll just, well, okay. I mean, how big... Wait. How big is this? It's 300 by 300, right. Okay. So there's just this one number here, which... Fine. All right, well, let's copy this into input.text. Although, actually, I assume that my fetching input function will still work, right? Yeah, okay, cool. So we don't even need to actually build any kind of array at all. we can just have a function for computing the value, the power level of a cell based on its x and y coordinates. And then we can map that over all the XY pairs that matter, and then like move a sliding window over that map, kind of, right? Or not that map, that mapped list, that list of the power levels, list of lists. But right. So let's see. We want input is an int here. There we go. And let's say type coord again, coord a, well, whatever, coord equals int. We could use new types for x and y, I guess. But I don't want to. Seems like too much work. I think it'll be easy enough to remember. So the main thing here is just to define power level is a function from coord to int, right? And we can just transcribe this pretty liberally from the definition. So first we compute the rack ID, which we only need once. Power level of xy equals, let rack ID equal x times 10. Serial. So what do we need here? We need a base power of rack ID times y. It's x plus 10, not x times 10. Times y plus serial number times 10. Let's call this large, whatever. Equal base plus serial times 10. And then we need to choose hundreds equals large mod 100 div 100. In well, let's call it n, whatever. And we'll just take this whole thing. Minus 5. Okay, so we load this. Doesn't compile. I didn't delete. That's fair. So what I wanted to just check is what's the power level, say, of one of the test inputs they give us? Serial number 835. It's minus 5. This is incorrect. This is not what I wanted at all. Rack ID is x plus 10. Base is rack ID times y. Adding the serial number. Multiple. What is it I multiply by? Multiply by the rack ID. I saw ID here and it looks like the number 10, so I just multiplied by 10. But no, it's supposed to be ID. Okay. Now we get minus 5 still. Which is just as wrong as it was before. Increase the power level. Multiply it by the rack ID. Okay, so let's just say I took 1, 2, 3, 4, 5 here. This yields 0. Oh, well, yeah, obviously, right? We took it mod 100 and got 45. What I wanted was mod 1,000. This is still the wrong number. But why? Mod 1,000. It should be 345, right? Oh yeah, this is correct. And then well, no. That's 345, and then we take this and we div by 100. We get 3. But it's supposed to be... Okay, the rack ID is 13. Oh, I shouldn't have put 1, 2, 3, 4, 5 there, weirdo. Okay. Power level of... I forgot what I was trying to test. Of 8 and 3, 5. It's still minus 5. Why? Okay, power, we'll say power is this in, give me the rack ID, please. It's 13. That's what it's supposed to be. Next, give me the base instead. 65, that's correct. Uh-huh. Now instead, give me the large number. 949, that's correct. The hundreds digit of this should be 9. Oh, I didn't fix this. It should say... I can't... Ugh. Okay, we get 4. That's good. So, cool. Now we have this function here. Now what I'd like is a... what do we call these? They call it a cell... A square? So I want like square power. Takes an int and an input and a starting coordinate and returns an int. I'm thinking that we might someday want to do this for like a size of 5 by 5 instead of 3 by 3 or something. So square power of num cells. Well, it's not quite that, because the num cells of 3 by 3 is 9 technically, right? So let's call it width or something. Width serial top left. I actually need to take this as an XY equals. Sum of map power level serial over do let's let dx come from 0 up to width minus 1. And dy likewise from 0 up to height minus 1. This is inclusive, so that's why we need the minus 1s. And then we will just return x plus dxy plus dy. It's not height. And I don't want width. Oh, yeah, I just want width here, weirdo. There we go. What are you upset about here? I need to say pure. There we go. So that all compiles. What is the square power? We'll just run it on one of their test inputs. So fuel cell. So this is for a single fuel cell. For grid serial number 18, size 3. Top left corner of this. And then, oops. Paste. So this should produce 29. It does. Okay. Oh, oops, sorry. There you go. So now we just need to write part 1 to be iterating over all the valid pairs of coordinates and choosing the maximum. Part 1 of serial equals maximum by square power of 3 and serial of do. And let's go get import data.list maximum by while we're here. Maximum by also wants data ord comparing, because we don't actually want maximum by a thing. It has to be maximum by comparing this. Ooh, I didn't want to. I accidentally tried to run this as like eLisp code. Well, we won't pass 3. We'll say width again, right? But first we'll say where width equals 3. So first we will, let's see. And next, grid size equals 300. And now we need to know what the maximum offset is. Max offset equals, so if okay, let's imagine that the maximum size were 5, not 300, right? Then the valid starting points would be 1, 2, and 3. There are 3 of them. So that's our maximum width minus the width of a cell plus 1. Okay. So let's just choose x from 0 up to max offset minus 1. Interesting that I'm subtracting 1 here. Max init, let's call it, and then I can just cancel these out. Y likewise drawn from 0 up to max init, and then just pure of x, y. Doesn't like this. Couldn't match type int with int. maximum by what part of this? Oh, int is just wrong. Right? Yeah. So I can just say stack run input.text and get an answer. Oh, right, but now that I'm actually compiling it, I can't let these undefineds linger around. I need to like change my project template, but I made all the projects all like at once at the beginning, and now I don't want to go back and change the ones that I don't want to define. Okay, so 216.12. That seems pretty good. The XY coordinates of the top left fuel cell. Is that what we computed? Let's double check. Yes. Okay. 216.12. That's the right answer. Okay. Nice, easy warm-up. You discover a dial on the side of the device. It seems to let you select a square of any size, not just 3 by 3. Sizes from 1 by 1 to 300 by 300 are supported. Okay. So, okay, fine. There's a couple of things to point out here. First is we should git add this and git commit day 11 part 1. And the other is I didn't actually do the thing I meant to do, which was pre-compute the cells' values before mapping over them. We're actually like wasting quite a bit of computation doing this over and over. And it's going to get worse, you know, I would say about 300 times as bad if we just do this the obvious way. But you know what I will do, though, is first let's just try this with, oops. Well, I don't want to change part 1. I want to add part 2, right? I like my solutions to stand on their own when they're done. So really, I guess what I should do is write a function called best square that takes a few more parameters and then call that from both part 1 and part 2. So it'll take a serial number first. Let's not even give it a type yet. We'll do that in a minute. Best square of serial. Let's say grid size, because I don't know, we don't need it. Grid size is 300. So widths. Is that all I need, really? Sure. Equals this. It's a bit tricky because square power takes the width as a parameter, huh? I wish I could just like map. Because like the X and Y pairs that I want to look at are just... They have a fixed value, regardless of all this stuff I'm doing with width and what. Right? Like, and it's pointless to recompute them over and over. And so I sort of intended to, like, map a function over them before calling something like square power. But square power, like, produces its x's and y's by hand, and it can't really... I don't know. I mean, if I wanted to, I could pass it like an int map or something, which already has all the values computed, but it's just not that expensive to do some multiplications way too many times. So I'm going to just do it way too many times. And we just have to say width is drawn from 1 up, from widths, let's say. What I don't want is this, and I have to instead say I have to let this part be up here. Okay. So part 1 equals best square of 3. Ooh. Okay, so this is a bit yuck. I guess what I can do is just say comparing first, and then I'll produce a tuple of x, y, and square power with serial here. Okay, and now of course best square's type is completely messed up for whatever reason. Best square is a function taking a list of int and an int and producing a, oops, capital int please, a tuple of int and int. Now this is incorrect. First of all, we wish to compare second, and we want to produce the first of that. What? Square power doesn't have enough arguments, maybe? Correct. There. Now, does part 1 still run? Yes, and 216.12 was the correct answer. Okay. Now, part 2, I think, can just be best square of 1 to 300. And it has the wrong type. So I think that this should, in principle, run. I'm not sure how fast it will be. I mean, it should be 300 times as slow as the last one, right? There's a number of things that you could do to speed this up. The first and most obvious would be to build ahead of time a map computing the values, an int map, right? Containing the values for everything, for every x and y coordinate you might ever need. So let's do that, in fact. First. While we wait, right? I mean, maybe it'll finish and we won't need to worry about it. But in the meantime, let's do something simple. The more complicated and probably, in fact, more productive optimization would be some sort of dynamic programming thing where, like, we're recomputing many times the grid starting at 1, 1, for example, right? Because it's needed in... how do I get into artist mode? Is that what I'm thinking of? Well, not exactly. Whatever. My point is, like, okay, imagine that these 3 squares I've highlighted are part of the grid, and that I've drawn a square here instead of this weird wonky thing. We have to compute the grid here, like, and its sum many times for, like, this position, and for also the one that goes a bit below it, and for the one that goes a bit below it, and the one that goes a bit below it, and the one that goes over here to the right. Like, there's a ton of wasted effort computing the size of that section. So I assume there's some sort of dynamic programming optimization you could do where you save a table of previous results you've had, and figuring out exactly how to make use of that table is a little bit less clear, but, like, you could build one anyway. But the first thing to do is just do less pointless arithmetic. So let's fix that. I don't think that'll help too much. Why are you upset? Oh, because I haven't restarted Intero? Okay. So what I would like... really stinks that square power takes a width as an argument. Because really... power level is what I want, right? So maybe what I should do is erase square power as a function. It just shouldn't exist, I guess. And I should just write best square in terms of power level. Okay. And let's choose dx. Wait. We already chose an x and a y. All right, I'm not sure exactly yet. So what we need though is we need memo, let's say. Or we'll call it power, right? Power is a map. I want like a map. Yeah, a map from int to the power level, right? So m dot maybe an int map is the wrong idea, and I should use a map of tuples, and everything would be much simpler. Yeah. M dot from list of tuple of coordinate and power level serial coordinate, where x is drawn from 1 up to grid size is typing, huh? And y likewise from 1 up to grid size and let coord equal xy. Okay, and then we just need m power of m lookup coord. Okay. So let's just like so fine. We'll just pretend to compute this and then throw away the result and return const 1 instead. I just want to confirm we didn't mess up part 1 with this change. Error. Given key is not an element in the map. Why? Oh, well, x started at 0 and it should have started at 1. That's the main question. So from 1 up to max init, okay, sure. A completely different number. Fascinating. Why? Power level takes a serial number and a coordinate. So like that's all still fine. Oh, well, yeah, I didn't make a square yet. So for each width and widths, we need to do this. W is not width. It's, well, let's take a dx, right? From 0 up to width minus 1. dy from 0 up to width minus 1 also. X plus dx, y plus dy, but this is not correct either. Because really we now need to do some summing up of things. So let's say pure sum of do I don't want sum. I want fmap sum, I guess. No. I want pure of a tuple, xy, and sum of do. Ugh. Okay. Doesn't feel good. And it's still not really going to lend itself to being memoized in the best way. But okay, we're back to getting the right answer at least. So now I've leaving this running is going to be just as bad. It won't be any better. But I just wanted to do that because at least we're wasting less work this way, right? We just do a couple map lookups. I don't know. Maybe that is slower than just doing a few multiplications. Isn't it? It must be slower. This whole thing is just a pointless faffery. What we really need is a way to make use of previous work. And this problem just begs for some sort of memoization. And you could probably I'm not that great at dynamic programming. I've written a few such things, and on simple cases that look a lot like things I've seen before, I can figure it out as long as the cardinality of inputs is low. But when it gets to be there's a lot of inputs, I get a little confused. So, however, I think we can probably just use actual memoization and be kind of okay. I guess something to think about is how many... So, okay, here's the thing. In order to compute the size of a square, we can just say, what is the size of a slightly smaller version of that square? And then, add together the size of the strip that we need to add to that, right? So my question is, how many subsquares are there inside of this big old square that we have? Because if that number is at all manageable, we can just save all of them. And if it's not, we're going to have to do something fancier with dynamic programming to save only the stuff that we still need. But I'm not actually sure... what are the inputs that we would want? How do we define a square? Or not a square, but a rectangle? Because everything we want to look up is a square. But... well, I was imagining we would take the square... and say, okay, well, I've computed the size of this square. Not the size of this whole square, but say I had been asked. It's I don't have a good way to draw. I know I can just put text on the screen. Fine. So let's say we have let's say we want to compute the size of this whole thing. Not the size, the power level. We could say, well, this large square is really just this smaller square, 1, 2, 4, 5, plus this fringe here, right? And we can assume by recursion / induction that we already know the size of the smaller square and just go look it up instead of recomputing it. Then we would only need to compute the size of this fringe. Right? But the size of the fringe is a very specialized thing to need, right? if we have a square, you know, that looks a little bigger, like A, B, C here, this specific fringe of 5 numbers will only be used when computing the size of this specific square of 9 numbers, right? I won't be able to reuse any of my knowledge about this fringe to compute, say, this fringe. Well, I guess I don't need this fringe, but... when I want to compute this, well, I don't know. Maybe that's all right. I was imagining, though, that I might say, okay, well, to compute the size of a square, first, compute the size of the smaller square to the top left of it, which is easy. And then add, like, the size of this rectangle and the size of this rectangle, which would sort of be useful, right? We could, in principle, make use of this rectangle when we're computing, say, right? This rectangle here would still be useful if we needed to compute, like... Well, maybe it wouldn't. Okay, so maybe I should just say, like, that the important savings to make is calculating subsquares. And you know what? We'll just waste some duplicated work on the fringe of all of these. Right? And like as the square gets large, that's where all the expense is coming from, right? Let's say the square that we're looking at to sum is like 20 by 20. Then the area of the square, the number of multiplications of this subsquare, or no, calculations, whatever, that we have to do on the subsquare, is like 19 by 19. Whereas this perimeter that we're saving on is just 20 plus 20, roughly. 20 plus 19 probably, but so we get the majority of the benefit by not bothering with this more complicated rectangle approach. Okay, so this is just like never gonna complete, so let's not bother. So my thinking is to say we need some more powerful stuff here. I mean, not really. What we need is a map containing three tuples, right? It takes or a tuple of a pair of pairs, which is sort of the same thing as a 3-tuple. No. Of course, there would be 4 things in a pair of pairs. We want a pair of int and tuple, which is the same as a 3-tuple. And that will be the key in the map. Coordinate and size. And we'll store in there its the sum of all of those things. Okay, so we can reuse this power thing that we have here. That's no problem. It's already pre-computing the power for an xy coordinate. But now we want something a little more advanced. We want subsquares is m dot from list All right, I think you guys are going to get to see some fancy juju here. Let's let chords equal all the pairs of xy coordinates we can make, and then I can just reuse this for coord in coords. Fine. Now, for every... What exactly do I want? Right, I need to make like, okay. So a list where the key is a coordinate and a size, and the value is square power of k, where chord is drawn from chords and size is drawn from widths. Let k equal this. Okay, and so now we have not yet defined square power, and that's the interesting one. Square power takes a coordinate and a size, right? Well, let's be a little bit more exciting here. Let's say that square power of coord 1, this is the base case, right, is equal to just power level of serial coord. Yes. And square power of k as coord size is something else. It's equal to so we've chosen a coordinate and a size which is greater than 1. So what we need to do is let what's the opposite of a fringe? Base? I don't know. Let base equal subsquares looking up chord and size minus 1. So we're going to look up in our map the size of the smaller square and save that. And then return base plus sum of do should this even really be a do? Let's just write base plus sum of this list comprehension, right? Power level serial chord serial level of chord prime, where this sucks. Okay, well, actually, what I should do is base plus sum of map power level serial over the fringe of chord and size. Okay. So this is all fine. Also, I'm not using k anywhere. Why is that? Interesting. I guess I just don't need it. Okay. Now we need this function called fringe. Fringe of x, y, and size is equal to... God, this function is getting messy. But a lot of the stuff up here is going to get removed. I just like have to finish writing out all these. I keep assuming functions into existence, and then I have to actually justify that assumption by writing them. I don't want to go back to the stuff I was working on earlier till I've got all this stuff out of my head. So here, I just want to... power level... Oh, right. Power level just... I don't have a map of XYs that I need to pass around anymore. Right. I just have like an XY pair, and we can compute the power level from that directly. I don't have to like pass chunks of the grid into this fringe thing. So I just want fringe to produce a list of coordinates that are equal to like the area you would trim off of this by making a smaller square. And so it really is just like, let's see, let's do the right side of the fringe first. It's x plus size. So let's see, if the size that we had were 2 by 2, and we wanted the fringe of that, it should only add 1. So let's subtract 1 here. X plus size minus 1, and give me the right side. Y dy, where dy is drawn from 0 up to size minus 1 plus the same thing. Well, let's use whatever. We'll use that. Same thing as plus plus. The same thing, but on the y side, and we're going to subtract. We're not going to double count the corner. I have to like write a thing here, right? Yeah, what have I even drawn here? I guess I needed that. Plus x plus dx and y plus size minus 1, where dx is drawn from 0 up to size minus 2. So let's test this. In fact, this doesn't even need to be local to this. So let's extract as many of these as we can to be global functions. Yeah, this is the type that I want, please. Oh, only it's chords. So does this actually like this compiles, which shocks me. But what's the fringe of... what does it want? It wants the coordinate first. The fringe of 1, 1 for a square of size 2. So I believe this should produce 1, 2, 2, 2, and 2, 1. Fine. Different order, but that's fine. That's what I wanted. So we kind of need square power because it's closing over serial and over subsquares. I'm actually like, okay, well, yeah, it compiles, but we don't make use of square power or anything. So we kind of need to fix this whole thing, right? We need widths, X and Y. And then we just need to like get rid of all this crap. And we don't need power for anything, is that correct? Yeah, we're not using this anymore. Well, actually, we could be. Although honestly, like, it's probably faster to just call the power level function than it is to look something up in this stupid map. X, Y, and then just look up the score in square power. Square power, that's what I called it, right? Yeah. Square power. And we want to look up chord and width. Couldn't match. Square power is applied to too few arguments. What type have you inferred for square power? Well, that's true, isn't it? I meant to look up in subsquares. Although I could equally have looked up in square power, I suppose, as long as I called it as a function instead of as a... Okay. I mean... I don't expect this to exactly be correct, but I'd like to see what happens. Loop. Okay. Well, that's fair. Oh gosh, I need a lazy map. I'm relying on laziness this whole time. Yeah, try again. Call stack error. Not an element in the map. Well, this is the problem with looking things up using cheating operations that could fail like this. I should do things better. Then I would at least know what wasn't there. So when we build the list, one up to grid size. Those look fine. So the coordinates are fine. square power takes a coordinate and a width. Well, okay, so here's a thing. This whole business here is like no longer necessary, is it? No, it kind of is, because I don't want to just look up the largest element in the map, because that could include squares too large for our legal set of widths, right? Well, no, because we're drawing from widths down there. Yeah, this should be fine. I can just look up the largest element of the map. Of m dot this of sub squares. Wait. Subsquares. Why is this wrong? Int. Oh, yeah. Our key is a pair of coordinate and size. Okay, I assume this is still broken? Or it gives me the wrong answer anyway? Yeah. So, when I said you were going to see some, I don't remember what I said, deep doo-doo maybe? What I meant was that I'm building a map which refers to itself circularly. It might have slipped by you, but subsquares is defined as from list of this list comprehension, where the key is some key, and the value is calling square power on that key. Square power is a function which takes a key and sometimes just calls power level on that value, but other times it looks up a value in subsquares. And I just assume that value will be there. And that's okay, because actually it will be. I mean, except of course for the errors I'm getting about stuff not being in a map. But I'm lazily calling, my plan anyway, was to lazily initialize subsquares with every value I ever plan to look up in it. And the value I'll put in is square power of k. And by laziness, that square power of k doesn't actually get called until it's needed. So the map is just full of thunks. Computations that are waiting to be needed. And when I need one of them, by this stuff up here, then it will be forced, and that'll be a call to square power, which will probably involve looking up in subsquares a smaller version of that question, right? A smaller piece of that square. And that probably won't have been forced yet either. So that thunk will get forced, and it'll sort of telescope down to smaller and smaller versions until finally we get to the base case, and then all of those entries have been updated in the map for future use. That's what's supposed to be happening. but it's not actually happening. I'm not entirely sure why. I mean, it really, like, it has to be this. This is the only M lookup that we're doing. Okay, I mean, I guess we can just, like, cheat a little and import debug trace. I'm not very good at debugging Haskell. So let's just say, what the hell is in debug trace? I don't know. Trace show, I think? Trace show, yeah, sure. Takes something that you can print and a value and returns the value, but prints the printing thing as a cheaty side effect. So what I want to do is just trace show of k applied to this. And this will print out every coordinate we look up, and I can see what the last one was, and hopefully that's where we crashed. The very first time we tried to look something up. Well, why isn't that an element in the map is my question. 1, 1, 3. I should be able to prove that that is in the map, right? K okay. Trace show id of this. So let's print the map out once. And it should be gigantic. Actually, it should break, right? It didn't do anything? How could you not print anything? Is it never used? Did I make some kind of crazy mistake? Sure looks used. Trace show ID. Debug trace. Trace ID. Trace show ID. Prints a thing. Uh-huh. Yeah, that's what I wanted. When I try to show, okay, well, let's get rid of this and confirm that indeed we are somehow not showing anything. Loop. Now that's an interesting outcome. Okay, let's trace show instead this is not going to work either, is it? M dot what data map Haskell data map strict. We actually want lazy. I want to look at the keys. Oh, it is just called keys. Okay. M dot keys of trace. What are all the in debug trace? Is there some kind of like I can call a function on the thing? Trace M, trace show. Not really. Because what I want to do is look at the keys of it, right? Well, okay. Let's trace show ID of k. What are all the keys we're adding to this thing? Should print a lot of things. Yeah. It printed like... Ugh, I mean, I guess I actually need to type this to less, but... Oh, right, it goes to standard error. So 113 gets put into the map. That's fine. Oh! Ha 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 ha. Ah ha 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 ha. The problem is that our list of legal widths, in part 1, we don't actually use the sizes of all of the things, right? Only 3. And so we never actually put 112 into the map. That's kind of funny. Well, I was hoping to use the same code for parts 1 and 2. It's a bit awkward, I guess. Okay, well, first of all, this was wrong to begin with. Should have been 298. We can't have a width that's larger than that. Let's just comment out part 1 and see if part 2 works. Because part 2 does actually, like, that assumption should hold. I never actually printed anything. It's not crashing immediately, right? So we don't seem to have any circular references. Okay. Well, that's nice to know. I sort of thought that it would be much faster doing this. And it is. Or, I mean, I still think that. How are we doing in terms of, like, memory? I just saw 400% CPU. That's a little surprising. Resident size is actually not climbing, is it? It's 7.4 gigs, which seems pretty dang large. But we seem to be staying at that size, so at least it's not like... I think that what has happened is it's allocated a whole giant map full of thunks, and they all refer to each other, and it's busy like chewing through that map, resolving one reference, making it resolve another, and so on. And so memory is not growing, right? It's just replacing pointers with ints, or pointers with pointers to ints or something, whatever. How many entries actually should it have? I mean, our keys are triples of ints. Hang on, are we doing way more work than we need to? We are. Because I'm computing things like the value of a square that starts at 298, whose size is 298, right? Stuff like that is totally wasted work, and there's a lot of it. So what I need to do is fix that here, right? This is where I compute the list of all things I might ever need to know. And so, in fact, we might as well stop this because it's going to get a wrong answer when it's done. Now, here's where I need back the part that I deleted earlier, right? From list, and we'll just say do here, because it's going to need to be a bit longer. Width drawn from widths, and now we need, we don't just want to reuse all the coordinates, right? We need x drawn from 1 up to grid size minus width plus 1. Likewise, y from this same thing, and we will pure, well, let's let this, and then pure this, and it's not size but width. Oops, deleted too many lines. Okay. Am I even using coords here? I'm not. All right. Well, this should. Don't pipe it to less, please. I don't need that kind of stuff in my life. That was more useful when we were doing debug tracing. Although, to be honest, maybe I should still be doing some debug tracing, right? What exactly is it that I want to show? Let's just show the... No. Let's just show the key we're making. And like confirm that we're building mostly reasonable things. And see what kind of progress we're making as well. Yeah. So it's building like, oh my gosh. 300 by 300 by 300 though is only like less than, it's what? 27 million is what it is? So like, I'm probably not going to get through it by just holding down scroll, I guess is what I'm really ought to be learning. I mean, it seems to be building all the right entries. There's just a few million of them is all. Less, really, right? I wish I could like print some progress, but since I'm... all of the computation is happening inside the Haskell runtime, right? not much of it is actually happening in my program anymore, in code that I wrote. I've set up 1,000,000 thunks, 27 million thunks, and said, hello, Haskell runtime, please add them all up for me. And when they get... When they get actually resolved is pretty unclear. You know, let's do something a little bit... What I want to do is... Let's compute this. Trace show ID. I don't know. Let's just show what we've actually resolved, right? And that way I'll get an idea of how fast it's going. What coordinates it's actually working on. I see. It hasn't even gotten as far as operating on anything. It's just piling a bunch of thunks into this giant map. Oh! Now it's going. And it's going through them actually, like, shockingly quickly, all things considered. Given that it has to actually print them as well? It's doing pretty well, I would say. Let's make sure, while we do this, that we're actually, like, printing the right thing. It would be quite embarrassing. But maximum by comparing second, that's the value that we found of the subsquares. And the subsquares are guaranteed to include the thing we want. And then having gotten that, we call first getting the key, and then first again getting the coordinates. Let's confirm that that's what I want. Oh, it's not. All right, hang on. Take a break, Haskell. I just want... I want more than this, right? I want a pair like this. And it seems to be doing pretty well, so I'm not going to trace show ID this anymore. I'm going to let it go a bit faster. It's still, like, going to take many minutes. Oh. Yeah. So, oh, hang on. You guys couldn't see that. I just had to adjust the types. It doesn't return int to int. It returns int to int to int now. And I had to remove one of the two firsts in this section so that we're getting back the whole key, which is an XY and an int, rather than just the XY part. And I mean, it's going to be really slow. I don't need TPO, please. Interestingly, our resident size has not gotten as high as it was before. But okay, it's still growing, which I think means that it's still busy building the map and not actually filling it in yet. I mean, it's gonna be a while. And I mean, I'm sure there's some way we could have done this without needing such a gigantic memoization table. But it kind of looks like a three-dimensional problem, doesn't it? Well... I don't know. Oh, is it done? It looks done. Did it crash? Or, no, it gave me a value. How exciting. Okay, so let's type this in to advent of code here. And it doesn't want these. So X, Y, size. Submit. That's the right answer. All right, so I don't know if that was elegant. Some parts of it were. I mean, let's close the top window, git add. I mean, I probably just want to add all of this, right? I guess not, actually. Don't add debug dot. Oh, yes, add data map. Don't add debug trace. Oh, we didn't ever fix part 1, actually. Well, how would I go about doing such a thing? Oh, that should be easy. I can just call find with default and if it's not there, just compute it directly. But but there's no. I don't actually have that. I don't have a function that computes that anymore since I deleted the square power function. Well, you know what? I bet that there is no 2x2 that's better than the best 3x3. So I'm just going to say 1 up to 3 here. So if I say run, do I get out my results for part 1 again? 21612, that looks familiar. Okay, so this is not strictly speaking correct. We can leave a little to-do here. To-do best square of just 3 should work. But doesn't because it assumes recursive subcalculations will be done. Okay. Fine. Now let's get back to git add here. Actually, git checkout. Yes, throw that out. Okay. Yep. Git commit day 11 part 2. So I think that the most exciting part of this solution was like the mutual recursion between these two things. I'm always very pleased in Haskell when I can. It's difficult to do memoization in a purely functional way, right? In, say, Java, you can have like a map of from function input to function output that wraps a function, and when you would call the function, first check the map. If it's there, return the value. If it's not there, compute it and put it in the map, then return the value, right? And all of this is fine in Haskell, except for the words put it in the map, which like you just can't do. If you're saving a map, you can't modify it. And sometimes this is like a little bit hard to work around, and you can use like an stref or something like that. I don't know, some ref to let you actually modify things. But quite often, I have found, you can work around this by building the entire map that anyone might ever want ahead of time, and allowing laziness to only actually call the function on inputs that someone wants the value for. That's what we did here, and I explained that somewhat, but maybe not in enough detail. So subsquares is a map whose key is an input we might call the compute square function with, and whose value is the result of calling the square power function, right? But square power looks up a solution to its subproblem in subsquares, right? And so these two things refer to each other. But since I never have to modify anything because I filled subsquares lazily with every input it will ever get called for all at once. And then I just set off the recursive call and said, hey, show me all the values in this. And let the Haskell runtime system untangle all the thunks pointing to each other. The mutation in this case comes from the Haskell runtime system, where values begin their life as thunks, ways to compute a thing, and then when you look at them, they transmogrify into the actual value of the thing. So we filled the map up with thunks, and then we started resolving them to get our answer. And it's a really cool way, I think, to do memoization. It doesn't, like... Definitely you would want something more advanced for, like, a real production app. Like, it should have an eviction policy, for example. Like, that's a pretty fundamental requirement. Here, like, it actually took us a really long time to even build the map and fill it with thunks, because there were, like, a large number of inputs you might call it on. And we were just taking 3 ints from 1 to 300, right? Like, if your function could be called on any string, like, you just can't do this. In principle, you can do it for anything which can be converted to an int. And a while ago, I built that as an exercise. It would, like, took any enum input and built the tree of, like, all the enums that could ever exist in the world. And when you called that function, it basically was searching through that extremely large tree. But I built it in such a way that you didn't have to go too deep. Anyway, so yeah, that was the idea, was to compute the size of a large square. You look up the size of a smaller square, which you've hopefully already done. Although, like, really, this didn't help us as much as I would have liked. Yeah, we really didn't get as much out of this memoization as I had thought. It maybe made the program, what, like 20 times, or, 300 times faster? Because for the squares of size, say, 298, there's only one of them, right? And you can look up the size of the square of size 297, and, like, it's great that you didn't have to compute that again. So, like, you build you compute one fewer list of size 297. I guess there are a lot of subsquares. And they don't all have the same origin, right? They don't all start at 1, 1. So there are many, many squares of size, say, 150. Because it can start at, like, half the positions in your whole square. And for many of those, there are larger squares that would be repeating that work. So I don't know. It probably actually saved us more than 300 times. I don't know. I think something involving rectangles would still be faster somehow. But I don't see exactly how to do it. Anything else of interest to talk about here before we go? For lists, monoid append here is the same. I mean, now it's semigroup, but it used to be monoid. Is the same as plus plus concatenation. Lists form a monoid under concat, and so this is the same as concat. Or well, append I guess is the right word, right? This is append. Concat is a different thing. In Clojure it's called concat, but here it's called append. Yeah, I mean, really the whole thing was about building this recursive map. All right, cool. Well, I guess we're done. Thanks for watching, and I'll see you next time.